Hey everyone, Mr. Andrew here. Today I want to talk to you about ionic compounds, mainly what they are, how they're formed, and ways that we can identify what their formula is going to be. So, ionic compounds are new substances that form between the bonding of positive and negative ions. Now, we call these positive ions cations, and we call the negative ions anions. And these two ions are formed when two elements exchange electrons. Whatever is going to become the cation loses its electrons, and the anion takes those in. And as a result, both become more stable because they're both meeting the octet rule. Now, there are a couple main rules for forming ionic compounds. So, okay, so there's two main rules. The first rule is that they must be made of a metal cation and a non-metal anion. Okay? And the second rule is that they must be neutral. Okay? So, you have to have a metal cation and a non-metal anion, and as a result of this reaction where electrons are exchanged, the resulting products must be neutrally charged overall. Okay? So, let's look at a couple examples of this. So, first let's look at a simple one. Sodium and chlorine. Okay? So, if we look at the Lewis dot structure, sodium, just start with the symbol. Because sodium's right here, it's going to have one valence electron. So we're just going to put a dot right here. Chlorine is all the way over here in group 17, which means it's going to have 7 valence electrons. So we're going to put it like this. 2, 3, 4, 5, 6, 7. So remember, with these Lewis dot structures, you have to have one on each side, top, bottom, left, and right, before you can start pairing them. Okay? Now, when these two react, sodium is going to donate its electron to chlorine right here. Okay? Now, as a result of this, sodium is going to have a +1 charge. And that's because sodium has lost a negatively charged particle. So because of that, it's slightly less negative than it was at the start of the reaction. Chlorine, on the other hand, is going to have a -1 charge because it gained a negative particle. So now it's more negative than it was at the start. And we could actually get this information from the periodic table because each element in a particular column will end up having the exact same charge when it forms an ion. And all of these are dictated by the octet rule. So all these in group 1 will all end up with a +1 charge. All these in group 2 will have a +2 charge. Just quickly clean up that arrow so it can be out of the way. All these in group 13 will have a +3 charge. We're going to skip the group 14 elements right here because the octet rule says that these could either gain or lose because it's equally distant from both 0 and 8, so we're going to skip these. All these in group 15, because they have 5 valence electrons, we're going to have a -3 charge, and then the pattern basically just holds. 6 is -2, 7 is -1, and then these ones have a 0 charge because they don't want to form ions. The octet rule says they're already stable with 8 valence electrons, so they're going to stay right there. Okay. So these are my ionic symbols. Sodium has a +1 charge. We can see that right here at the top. Chlorine has a -1 charge, and we can see that right here too. Okay. So next, we want to look at what these are going to look like when we put them together. Okay. This is the ionic compound formula. And when you stick these together, you end up with NaCl. Okay. And for the name is sodium chloride. So remember, when you're naming these, the cation stays the same. The one that's listed first has to be the cation. The name for the cation stays the same. Okay. So here we have sodium, and it's listed as sodium. The anion, which is listed second, has to change to the ide form. You have to change the ending to the IDE form. So chlorine becomes chloride. So let's check these rules, make sure that we abided by them. So do we have a metal cation and a non-metal anion? Sodium is definitely a metal, it's a group 1, and chlorine is definitely a non-metal, so we have met those criteria. Also, it must be neutral. Now, the neutral rule basically has 2 pieces to it. It means that the number of electrons lost by the cation has to be the same as the amount gained by the anion, which this is true. And also, the resulting compound has to be neutrally charged overall. If we look at it, sodium has a +1 charge, chlorine has a -1 charge, so these two would cancel each other out, and the result is this compound is neutral. Okay? So let's look at another one. Let's do this instead. Okay. This time, let's look at lithium and oxygen. So lithium is another group 1 element. So its Lewis dot structure is going to be Li with a dot. Oxygen is a group 16 element. So it has 6 valence electrons. So it should end up looking something like this. 2 sides have a pair of electrons, 2 sides have single electrons. Now, what makes this one different from the last one is that lithium right here can only donate 1 electron. But oxygen still needs another one. Okay, there's something missing right here. So how do we solve this problem? We just add another lithium. Now this is allowed because when we're talking about this reaction, we're focusing on just one copy, okay, one oxygen reacting with two lithiums. But when you're dealing in the real world, you're dealing with millions and millions and millions and millions and millions of these particles interacting with each other at any given time. So as a result, it's not hard for us to end up with 2 lithiums or 5 lithiums or 100 lithiums, because you're always going to be in a situation where you have way more lithiums than you need. So the symbol lithium is going to be Li, and just like sodium, because it's in this first group, it's going to have a +1 charge. Oxygen, because it's in this group 16 with 6 valence electrons, it's going to have a 2- charge. Now, our ionic compound formula is going to be Li, and there's 2 of them. Oh, okay. The little subscripts right here tell us how many copies of the element that comes before it are present in this molecule. So this 2 right here says that there are 2 lithiums. Because oxygen has nothing listed here, right? That means that there's only 1 oxygen. Okay? And the name for this is lithium oxide. So let's check and see how we did. Metal cation and non-metal anion. Lithium's a metal, oxygen's a non-metal, so we're good on that one. Must be neutral. Lithium, these 2 together are donating 2 electrons, and oxygen is gaining 2 electrons. And if we check the charges right here, lithium is 1+, oxygen's 2-. But because we have 2 lithiums, we have to multiply lithium's charge, which is +1, by its subscript. So 1 times 2, that's 2+ overall. So now we have 2 positives and 2 negative charges. It means overall this is neutral. Let's look at one last one. Okay. Let's look at one that's a little bit more complicated. Let's look at magnesium and phosphorus. Okay. So magnesium is in group 2. So it's going to have 2 valence electrons. Phosphorus is in group 15. So it has 5 valence electrons. So let's just start with what we got so far. Magnesium donates its 2 electrons to phosphorus. But phosphorus still wants an electron. So we're going to add another magnesium. Magnesium donates 1 to phosphorus. But now it's got an extra electron it wants to donate. But this phosphorus can't take anymore. So we're going to make another phosphorus. Okay. It donates 1. But now phosphorus still wants 2 more electrons. So we're going to make 1 more magnesium. This magnesium donates its electrons. And now both of these phosphoruses meet the octet rule because they've both gained 3. First one, 1, 2, 3. Second one, 1, 2, 3. And all of these magnesiums also meet the octet rule because they've all donated their electrons. So all of these meet the octet rule, they're all stable. Okay. Let's give myself a little bit more space here. Okay. So the symbols are going to be Mg 2 plus and P 3 minus. Now there's actually a quick way that we could have figured out that it was going to end up this way. See, because when we're trying to write the formula for ionic compounds, there's actually a strategy. This is sometimes called like the crisscross strategy. But here's how this works. When you have two elements that are going to bond together that have different charges, and by different, I mean they're not balanced, what we can do is we can take the number from the charge of the cation, and that will become the subscript for the anion. And we could do the opposite here. We take the number from the charge of the anion, and this becomes the charge of the cation. I'm sorry, the number from the charge of the anion, this becomes the new subscript for the cation. So when we do this, our formula is Mg3P2 because magnesium's new subscript right here is the number from the charge of the anion. And phosphorus's new subscript right here is the number from the charge of the cation. And the name for this is magnesium phosphide. Okay. So let's check this. Metal cation and nonmetal anion, definitely. Must be neutral. So we showed earlier in this top section that the number of electrons lost by magnesium is the same number that was gained by phosphorus. And if we look at the charges, magnesium has a +2 charge, phosphorus has a 3 minus charge. But we have to multiply these by the subscripts. So 2 times 3, that's 6 positives. -3 times 2, that's 6 negatives. 6 positives and 6 negatives, those cancel out, so we are neutral. So this is a strategy that we can use to comfortably diagram out how ionic compounds are going to be formed. Hopefully this video was helpful to you. If you have any questions, stop by and see me anytime, and I will see you next time.